Oh.
How are you? I'm just good. Wait, what? Seriously? Just one day every week. Looking good, Lucas.
Awesome. Thank you, sir. Okay, so let's take a quick look here. Let's look at some stuff relative to satellites. So we've determined we've talked about Kepler's laws. We now know how to the first assignment. It's all pretty much the same stuff. You're using Kepler's third law, which is just the fact that we know that. Well, what you tell me real quick. What's Kepler's third law? T1,
T2, R squared,
equals
R1 over R2.
Squared.
Cubed.
I was trying to help, guys.
Well, you weren't.
I know. True.
Okay, so
Gotcha.
there's Kepler's third law. So you're using that to compare the motion of the orbit of some unknown object whose parameters aren't known to one that is. Like for example, we know what the moon's period and radius are, radial distance are, so we could use that information to calculate a missing parameter for any other satellite, right, by comparing it to the moon. Okay? That's what that was about largely. The other thing that we introduced, we haven't really done anything with yet, but we talked about the other day, was the law of universal gravitation. That's a big one. So that's the one that says the force of gravity equals what?
M1, something about that.
You're right. M1, excuse me?
M2 over T.
No. R squared times
Constant.
capital G. Good. Okay. So that's where capital G is the universal gravitation constant. M1 and M2 are the masses of the two objects that are gravitationally acting on each other. And then R is the distance between what?
The center.
Centers of mass. Good. So the centers of the object. Typically, centers of the objects. Good. Okay. So what we want to do today is we want to sort of combine. We're going to use both of these concepts a little bit, and we're going to go back to our understanding of circular motion, uniform circular motion. And we want to come up with and be able to use some, I think, we didn't get through this the other day. We want to come up with and use some equations that predict for a satellite what its velocity would be based on its period or based on its distance from the Earth. We want to know what its period would be based on how far it is from the Earth. Things like that, right? So how can we do that? If I've got a satellite in orbit around the Earth, so here's the Earth, and here's my satellite, and that distance is R. What can you tell me about that satellite? About the force acting on it?
What do you mean?
What is the force acting on that satellite? If we just say that, we'll call M sub s the mass of the satellite.
Gravity.
Okay, so it's going to be gravity, and it's given by that, isn't it? Right? That's what this is good for. This is the equation, the law of universal gravitation that dictates how strong a gravitational force is between objects. How come it got so much harder than it used to be? It used to just be mg, small g. Why is that? Why do we have to have this thing?
Because we're not just dealing with Earth.
Okay, yeah, because when we're mg, remember with that only worked for situations where we're right at the surface of the Earth, where the radius is constant, right? So if we wanted to know what little g is, well, we could actually calculate the value of little g from this, couldn't we? Little g.
Hip hop star.
That's right. Physics hip hop star. So we know that the force of gravity on the surface of the Earth, the force of gravity is equal to, it equals g m1 times the mass of the Earth, let's say. Call it m sub e, the mass of the Earth, divided by the radius of the Earth squared. But it also just equals m1 times pseudo constant, lowercase g, right? Little g. So what can we do with this? algebraically, if I wanna solve for G, what's the only thing I have to do? Yeah, just divide away the mass of the object itself, and that's it, right? Little g we now recognize as big G times the mass of the Earth divided by the radius of the Earth squared. That's it. That's how we get little g.
Would it be the radius from the Earth center to the satellite?
Okay, yeah, but now we're talking if we're on the surface, right? Because little g wouldn't apply for a satellite, because gravity's going to get a little bit weaker as we leave the Earth's surface and go far away, right? Does that make sense?
Yeah.
Okay. So now we no longer can just rely on mg, because now we're talking about orbital physics, right? We're talking about satellites, and the acceleration of gravity is going to have changed a little bit. But what we could do is we could say for that satellite right there, we know that the force of gravity is that, right? It equals g m1 times the mass of the Earth divided by r squared, where r is not the radius of the Earth anymore. Now it's the distance from the center of the Earth all the way up to the satellite, right? Okay? Okay, so we also know, well, what kind of a force is that? If the satellite is moving in a circular orbit, how could we describe that gravitational force? What category? It's centripetal, right? It's centripetal, and so then because it's centripetal, we know that a centripetal force can always be written in terms of a centripetal acceleration. So we can also write it as m1 v squared over r, for example, right? Okay? Something really important we can do there. Algebraically, what can we do?
Solve for velocity.
We could, and we can cancel something, right? Yeah, we can cancel the m's. And so now, would you agree that now the quantities v and r are the only unknowns there? Everything else is a constant, right? And so because we only have two unknowns, algebraically we know that we could solve for one in terms of the other. And that's called a formula, right? So we can solve for v in terms of r or vice versa, right?
Will you remind me what M is?
What?
Mass of the Earth.
That's the mass of the Earth. Yeah, so 5.98 times 10, what did we say it was, times 10 to the 24? Something like that. A huge number, yeah. I think that's it. Big number. The book says 5.97. So now let's go ahead and solve for v, because that's an easy one. What's the only thing we have to do to solve for v? Good, multiply each side by r. So that's going to cancel that r and one of those. Everybody agree?
Yeah.
Okay, and then square root it, right? So a satellite's speed is given by, so we'll call it v sub s, equals the square root then of g times the mass of the Earth divided by r. Not the radius of the Earth, the distance it is from the center. What do you think would be the formula for calculating the orbital speed of a satellite around Mercury? Same, what's the only difference?
Mass of Mercury.
Yeah, instead of the mass of Earth, it'd be the mass of Mercury, right? Everybody see that? Okay, so this really is general. This m could just be the mass of the planet or the object around which it's orbiting, right? Okay, so that's a good one. What if we wanted to solve for r? Well, we can either go back to here and do it, or we could go from there, it doesn't matter, right? How about if we just square both sides to undo the square root? That becomes a v squared, and I just swap the v squared and the r. Everybody see that?
Yeah.
So we'd end up with the distance, radial distance of the satellite is equal to not the square root.
Yeah, just G
Yeah.
G times M over V squared.
Yeah, good. So it'd be g times v over v sub s squared. Right? Make sense? Okay, that's good. And then how could we? There's a number of ways we could do this. How would we maybe?
Wait, can you go?
Sure.
I just wasn't.
Sure.
Okay.
Let me get in that picture too. Yeah,
It's okay.
yeah, that's all right. Next time. All right. what about period? We could do the same thing with period, couldn't we? We could always, and I don't want you to, you don't need to memorize these. I never remember these. I just solve them for myself, just derive them anytime I need them, right? So this takes a second to do. How would we introduce the parameter t if we wanted to use that instead of like v?
Sub it for velocity equals 2 pi r v, and then
Yeah.
solve it for t and sub it for v.
Perfect, right, so then we'd go, then we've got the secondary equation we could use where we'd have speed equals 2 pi r over t. And so if I wanted to substitute and get t's instead of v's, I would just make that substitution, right? Every place I had a v, I would plug in the quantity 2 pi r over t and simplify, right? What if I wanted to solve, if I wanted to end up with the formula involving t's and v's? What would I do?
Like just multiply T.
Yeah, exactly. I just isolate r, right, and then substitute r. Do you get that? You're starting to see mathematically what, getting a better idea when we substitute what we're really doing. When we're substituting, we're always just making a variable change, aren't we? Like stuff like this. Okay. All right.
Wait, I'm just curious, so
Yep.
how did you know to set the universal gravity constant equation to the
To this right here.
Yeah, how did you know that they were equal?
Okay, because here's how we knew. Because the first question I asked you was, if this is the satellite and this is the distance from the center of the Earth, what's the force acting on it? Well, it's just that, right? Because it's dictated by the law of universal gravitation,
Oh,
which
that's
calculates
interesting.
gravitational force. But it's a centripetal force because it's moving in a circle, so it must equal m a sub c. Yeah.
Okay.
We also could, and we just have all kinds of choices here. We also could have written centripetal acceleration in terms of t and r, right? And that then we could have done the same stuff, right?
So do we know top full G?
Yeah. 6.67 times 10 to the minus 11. And the units or whatever makes it work. So, okay. It's in your book. You'll use it enough, you'll remember it. Use it quite a bit.
Gee, my bad.
Okay. So then let's do a little calculation here. I want to know. So we said the other day that that space in geosynchronous orbit, that band was really valuable. What would that nefarious terrorist organization, what kind of havoc would they wreak if they put a satellite in counter geosynchronous orbit? Meaning geosynchronous orbit going the wrong way.
And all the other satellites and UPDs are fine.
It'd be bad news, but how would they be going fast enough to cause any damage? Let's see. So we said, do you remember, do you remember how high it was? I think we said it was 43,015. Is that what it was? Does that ring a bell?
Yeah.
For the distance, kilometers from the center of the Earth?
Yeah.
Right, okay. So let's plug that in and find out what the speed's gonna be about, okay? So, just need a calculator. What do you think? Let's take a guess. We want to make an estimate. How fast do you think that satellite's going to be going in terms of kilometers per meter or per hour? How fast would the satellite be? Is a geosynchronous satellite traveling through space around the Earth? I mean, even just a regular one, right? You have to inject it into orbit with some speed.
567.
What is it?
567 miles per hour.
567 is what you think?
I think
Did you look it up?
Oh, no.
Oh, okay.
I think it would be the same as the Earth, so
That was close the way you said that, but I think you just.
Okay, let's see what we got here. Oh, gosh, why do you keep doing that?
I thought you said 600. So that's-
Okay, so here's our equation, right? We got the square root of, and let's go ahead and use our fancy fraction bar. We never used that. Oh, wrong one, right there. Okay, square root of 6.67 e negative 11 times mass of the Earth, 5.97 as the book says, E24, divided by the radius of, which we said was 43,015 kilometers, so it's going to be 43,150,000 meters, right?
What chapter is this in the book?
This is 8.
Chapter 8.
Okay? So that gives us about 3,042 meters per second. So it's going over 3 kilometers a second. That's pretty fast. That's fast, right? So not only is it going that fast, but if you put one in counter orbit, what are the relative speeds going to be? Twice that. Because one's going this way that fast and one's going that way. So it wouldn't take much. And we'll maybe make an educated guess about how big an object it would take to completely dismantle a satellite in about a chapter and a half. We'll be able to figure out what the energy carried by that object would be. And we could compare it to like tons of TNT even or something like that, right? So we could get an idea how damaging it would be. But you can already get a pretty good idea that that wouldn't have to be an extremely large object to cause some major damage, right? Just put that in terms of like compare that to the highest speed rifle you can think it would be. I mean, I don't know that much, but I'm thinking it would be like 4,000 feet a second or something like that. Would be really fast, really fast. So that would be just a little over 1 kilometer a second. So that's about 3 times as fast. And keep in mind, as we'll learn pretty soon, that the energy an object carries goes as the square of its velocity or speed. So if you make something 3 times as fast, you're actually making it carry 9 times as much energy. So that'd be a bad thing, right? You put a satellite going in the wrong direction, smashes into that thing, creates all kinds of little shrapnel, which flies out, sprays, and some of which goes into that geosynchronous belt, and you get a cascading chain reaction, and pretty soon it's unusable for a long, long, long time, right? All right, so hope none of you are terrorists, various terrorist types. So.
Well, not until.
Yeah, no thanks.
Now I know how to, I have another one.
Okay. Friday trivia? All right, so you guys have your physics books here? Okay, just make a note to yourself to, when you get a chance, in your physics book, just look on page 191, because that looks like the most interesting man in the world that's doing a really cool physics experiment there. I just saw that.
Is that you?
He doesn't always do physics, but when he does, it's gravitational physics. All right.
No. Oh, it's the most interesting man in the world. It's the most interesting man in the world. He has all these crazy stories about what he's done. He sells beer.
Yeah, we're going to talk a little bit here now. Okay, so where is my spray ball? Oh, there it is. Okay, so I want you to make a calculation here. Then I want you. Do you see that it would be pretty easy for us even now to calculate what the orbital period of Mercury should be?
Sure.
It wouldn't be a big deal, right? We know. We don't even need to know what its mass is. All we really need to know is how far it is from the sun, which we can easily measure. When it's, when it's sideways relative to the sun, we can see very, with high degree of precision, how far the centers of mass are apart. And all we'd have to do then to find out what its orbital period is just look at our physics book. It'll tell us, right? The orbital period, we didn't actually finish that equation, but if we had, we would have gotten this. If we had just done a couple more algebra steps, which we talked about doing, we would have found that the orbital period of Mercury is equal to 2 pi times square root of the radius of Mercury squared from the center of the sun over G times the mass of the sun. Okay? We could plug that in if we wanted to, and we'd get an answer. And that would predict how long it would take Mercury to travel around the sun once, right? If we could test all, we could do this for all the planets, and we'd find that they would all work, except that one doesn't work.
Because Mercury's weird.
Yeah, Mercury's weird. Mercury does not obey what classical physics tells us it should obey. It's a little bit different, which is bizarre. What's that?
It's a fact.
Yeah. People that had no explanation for this. We started to talk a little bit about this like a week and a half ago, 2 weeks ago, but I can't remember what it was. But anyway, it's people came up with these just bizarre. They had to try to find a way to explain this, and so they invented this thing called ether that permeates space. And Mercury was flying through this dense patch of ether, and it was just dorky and stuff that you just would laugh at now. That was the best guess at the time, until Einstein came along, and Einstein figured out what the problem is. It's not matching what the calculations say because we're not measuring the correct distance. We're measuring a distance in a flat space, but the space has been warped, and it's not a flat space. It's a curved space. And so we'd have to do a different calculation to figure out what value of R we would put into this calculation, right? So this is where our friends, the Flatlanders, come in. And they help us quite a bit with this, right? We had a little talk about flatland. You remember that. Flatland is, you hadn't known this previously, but this is just a little piece of flatland in my board here. It's truly two-dimensional. It's only got 2 degrees of freedom, right? Has no depth as we would see depth from our perspective, right? So we have to kind of try to wrap our brains around what Flatlanders experience a little bit, right? And this is where we kind of drew an analogy to people. We live in a 3-dimensional universe, but Dr. Monkman would tell us that we see pictures 2-dimensionally, but the way that we string them together in our evolved brains tells us that we can conceive pretty easily of the 3-dimensional space that we live in. We have all kinds of subtle cues that do that. The way our eyes focus, the size of something gives us a really good depth cue. Have you ever been or seen pictures where where's that crazy house? Is it around Salem or something? There's this house you can go to where it's all wrong. So you look from one perspective and it looks like that it's receding away, but it's actually just because it's an optical illusion. And if you have a person walk up what appears to be in the far corner, he looks like a giant. Have you ever seen that where it's just
like
I think so. I've never been there, but I've heard about it, seen pictures of it. It's pretty cool, but it's just what's going on there. Obviously, it's not. They bill it as being some kind of like a vortex or something, dorky like that. Something you'd see on Discovery Channel, showing the dorky stuff on Discovery Channel. But it's nothing like that. All it's doing is it's manipulating the visual cues that we normally use to judge distance, right? Into tricking our brains into seeing that as being this huge guy standing in the corner when he looks like he's 20 feet away, but he's only 3 feet away, kind of thing, right? So these guys would do the same thing, right? They experience their world a little different than we do. We can't totally appreciate what they experience, but we can get sort of a hint of it by maybe trying to immerse our head into their universe, and then if we did that, we would see their universe. We kind of talked about this. Maybe, your guess is as good as mine, but it seems like it would be kind of just like a white horizon everywhere. It would have no depth to it. But for us, then we would see Mr. Red as just a little red segment. When he gets further away, the segment would diminish. When it gets bigger, it would lengthen, right? If he had some kind of, let's say he had a little birthmark over there, when we walked around, we would see that little black line segment that would be his identifying birthmark, right? But if we went around the other side, it would disappear. Well, no, it's okay, it's just behind him now. We know about behind, so do they. But for them, the part and this is kind of important for them, because if you want to really draw the best, deepest conclusion from this cool talk we're going to have about this, because it really does give you a sense of what gravity really is, you still have to realize that we can never really communicate with these guys about what they see or what we see, right? Because every time we look into their universe, we're seeing that white horizon line embedded in space above and space below, right? They can't do that. You get that, right? They have no access to that dimensionality, and so they can't perceive it that way. For them, it's everything, right? It would be just like, when we look out here, it'd be like saying, okay, if we wanted to explain to them that, no, see, we're right next to you, but when I put my hand through into your universe, well, part of it's above and part of it's below, and those words would have no meaning to them. They would just think that I'm some bizarre creature that can morph its shape at will. Where I put my finger in, I'm small, but if I put my whole arm in, it gets a little bigger. The line segment gets a little bigger, right? They would have no idea that you say, well, just stack those up. Just stack those up like some coins or something, and then you could get a picture of what I'm like in 3 dimensions. That one, and then on top of that, put this next one, like if you look at a CAT scan or an MRI, how they just take little thin pictures and you can reconstruct it, right? But is that going to work? No, because once again, we're relying on the concept of above and below that they know nothing about, right? It'd be like saying, imagine when somebody has that conversation from Hyperland, when they're talking to us in Volume Land, and they say, they appear in our universe as being this 3-dimensional shape that changes, that contorts and changes, and they say, well, that's okay, just stack those up blob. If that's their word for the next direction that we don't have. But we can't do that, right? There's no way for us to conceive how you could somehow stack those up in a way that's going to give you an extra dimension, right? They've got an extra place to put a right angle that we don't have. In Flatland, they've only got room for 1 right angle, right? Well, we've got room for 3 in ours because we've got an axis that comes out of the board, right? See what I'm saying? They've got 2 right angle directions, we've got 3. All we got to tell them is, yeah, there's room for 1 more, just come straight out of the board. That means nothing to them. They can't see that space. The Hyperlanders would say to us, oh, you guys are so dumb, can't you see it? You go left, right, up, down, front, back, and blah, blah. And it's, we don't know what that is, though. There's no room for us to see where that goes, right? Okay? So let's explore what goes on then in Flatland. Flatlanders have the same problem with flat Mercury. Okay, if we look in Flatland, I'll use this as being, this will be the flat sun, let's say. And let's make this flat Mercury. So flat Mercury travels around their flat sun in a circle, like so. And these guys, they have the same, and they had the same problem until Flat Einstein figured it out for them, but they've got this distance from here to here that they can very accurately measure, right? The distance between the centers of mass. They're good at flat physics. They know what the universal law of flat gravitation is, and they ought to be able to determine what the flat period is of that flat planet, right? But it doesn't work. It doesn't work because they're not measuring the right space. Now we, however, can see that because this very dense and massive flat sun of theirs distorts their space in a way where it warps it into another dimension that they can't see, but we can fortuitously. If I turn their universe sideways, so if I turn their universe sideways, and let's say that this is going to represent the flat sun, so here's the profile of their, oh, that's not what we do. Here's the profile of their universe, right? From their perspective, here's what they would expect us to see. They would expect us to see their flat sun in profile, right? As I'm looking through the plane, it looks like a flat segment, and then Mercury, like so. And they would expect these distances to be the same as those. Anybody have a suggestion as to why maybe they're a little bit different?
Oh, just like, I don't know, like, if Mars like moves like up and down to us, then the circle segment will get smaller and bigger and smaller. Would that change the degree?
Well, here's what's going on. Now, they can't see this because their flat light travels in a flat straight line. It travels in a straight line in their universe, right? So if they want to send a photon from this point to this point, the quickest way to get there is like that. They can't possibly take any shortcuts. Light, by definition, travels in a straight line, in our universe too, right? So they're not going to notice, when photons travel from their sun to their planet, that is by definition a straight line for them, right? However, we see something different because in actuality what's happening is the gravity of their sun, that mass, is warping their space. So we would see the profile of their universe looking more like this. Or like that. Okay. Oops. Well, what's happened there? When we warped their space like that gravitationally, what did it do to that distance? Instead of being this far, all of a sudden it's actually that far. What's longer, the green arc or the black line? The green arc. Yeah, it is. And so what do you think really happens then when we made that calculation of, where was that? Right there. When we made that calculation of the period of Mercury, what was wrong with our radius?
It was for the straight line.
Yeah, it's too short. That's not the real distance. The real distance is different because the space is warped. And so that's going to make the period a little bit bigger than we would expect it to be, right? So it takes longer for Mercury to get around than we would suspect it would. And that's what we observed. When we look at Mercury, like let's go to flat Mercury as an example. When the flatlanders make the same calculation and they think Mercury should be there, well, it turns out that it hasn't gotten that far. It lags its calculations a little bit, right? And that was a huge mystery, but Einstein's the one that figured it out. The calculations that he made and the theory of general relativity that he developed, probably the single most amazing intellectual accomplishment of anybody ever. What's that?
It's like everything Einstein did was amazing.
Yeah, he was a pretty amazing guy. That allowed us to mathematically predict exactly where Mercury would be because he came up with the equations that predict how space is warped by gravity. There's some other things that happen too. I think maybe I mentioned this, I can't remember if I did or not, but there's some things you can observe that are really bizarre. If you look during an eclipse, if you look right by the sun, when the sun is blocked, stars that are not supposed to be visible become visible. Why are they becoming visible though? I mean, the star is supposed to be hidden. It's supposed to pretend this is the star, or this is the sun, and the star is supposed to be like right there. Well, turns out you can see it though. Why can you see it? The reason you can see it is because space has been warped so that now there is a straight line path between you and that star where it used to go right through the sun. See what I'm saying? It's like imagine stretching if you put say you had a latex mattress and you put grid lines painted it black, let's say, and you put grid lines on it, and then you put a bowling ball in the middle. What you're seeing there, you would see something similar to what we would see in flatland then. The surface is going to get stretched in some places. And so objects that, as you stretch out the space like that, it changes some of the straight line paths in that universe, right? Pretty bizarre. Because, and this is where people, hold that thought for 1 second, this is where people sometimes have a problem with that. Sometimes people say, okay, well, it's the gravitational warping. Gravity is just deflecting the light. But the thing is, gravity can't deflect light. Light has no mass, has no rest mass. And so like if I throw a ball to somebody, it arcs through the air because its trajectory is gravitationally deflected, right? It's got mass, gravity acts on that, and so it doesn't travel in a straight line. Light doesn't do that though. No matter how strong the gravity is, if I shine a laser beam in a straight line, the laser beam travels in a straight line. It is never deflected gravitationally. So how is it then that light gets bent by gravity? It's bent by gravity because the space the light is traveling through gets bent by gravity, right? There's a big difference there. You see that? Okay, this is,
It's like if it's a piece of paper.
say it again.
It's like if it was on a piece of paper. and you
Yeah,
cut the
yeah,
paper.
exactly. So, right, exactly. So that's a good way to think about it. So like this is, that's a straight line. Well, it's not exactly. That's a straight line in flatland, right?
Mhm.
That's still a straight line in flatland. Does it look straight to you now if I tip it a little bit? No. Do they see it as flat? Absolutely. Because from within the context of their universe, it's flat. Well, it's shorter in a direction that they can't travel, right? They don't have an option. They've got to travel through their space, right? And so as they travel through their space, which they perceive as being flat, then the line is always going to be a line to them, right? When people talk about hyperspace, and hyperspace is a real concept in physics. I mean, we talk about, and we'll spend some time at some point talking about parallel universes. It's entirely possible, and there are calculations that a lot of really smart physicists that with an entirely straight face will say that it's plausible and in fact sort of likely that our universe sits on the surface of a higher dimensional, what they call a brane, B-A-R-N-E, which is a manifold. It's the surface of a weird higher dimensional space. And that there's probably, based on these calculations, there's highly likely another parallel space to that might only be like 5 centimeters away. But it's 5 centimeters away through a space that we can't get through. But some of the phenomena in our universe might be explained by the interactions between matter in our universe and matter very close to ours, but in a different universe. And that sounds like a science fiction novel, but that's entirely,
Plausible.
I don't want to say plausible, that's what I was going to say. It's a hypothesis that might bear some fruit. It might turn out to be right. At this point, there's no way to disprove it. And there's some evidence mathematically, like your string theory, that says, yeah, it's kind of looks like that's not horribly unlikely. So, weird stuff. But the universe gets weird when you start looking at it through the eyes of physics. We're pretty mundane creatures. We live on a fixed scale in the universe. We're all, we might call it sort of a medium scale. But even in our own universe, when you look at things on different scales, things become pretty bizarre. And this is stuff that we know is 100% right. Quantum mechanically, if quantum mechanics were the prevailing physics on our level, well, life would be so different that it would be unrecognizable. But it would be no big deal for me to just stand here next to the door having a conversation. Next thing you know, I'm outside the door. That would happen all the time. I would just be here once and then be there. There's a certain probability I'd be here, and there's a certain probability the next second I'm sitting in my seat. I would never, ever pass through the space in between, but I would just either be here or be there. And that happens all the time on the quantum level. Now that's what's more bizarre. I mean, really
Is that like
think
with
about it.
electrons and stuff?
Yeah, that's what electrons do. Electrons, there's just another quick little example. Electrons, I know this is a little weird, but I just want you to get some idea that the stuff you learn here is very, very, yeah, it is. I mean, it's applied to our specific place in the universe, which is important, obviously, because we live here and it's nice for us to know how things work around us. But A, that's a very, very thin slice of what all scales and all energy levels of the universe are like. And B, it's all just kind of approximations that are good, but not perfect. Like all that stuff I told you about gravity was really a bunch of hogwash, turns out, right? Einstein had it right. This stuff, these equations work pretty well when we're not in the immediate vicinity of a black hole, but there are places in the universe where they don't work at all. Yeah.
So isn't it when matter goes from one place to the next? Isn't that quantum tunneling?
Quantum tunneling is, yeah. Quantum tunneling is an effect that's related to that, yeah. So here's what I was going to show you. If you look at a hydrogen atom, hydrogen atom just has the simple nucleus, right? So here's the nucleus, and then the atoms in a hydrogen atom, or the electrons in a hydrogen atom, the electron in a hydrogen atom, can take different, you might have talked about this, how many people had chemistry? So you've probably talked about like p orbitals and different shapes of the orbitals. So I think it's a p orbital, is that the one that has like the 2 lobes?
It's a-
S orbital? Okay, I can never remember. So in S orbital, there's like a cloud over here, a probability that the electron's gonna be, you know, over in this region somewhere, right? There's a cloud of probability it's gonna be over in this region. But there's a fairly wide plane in the middle where there's no chance the electron will ever be. It can't be there, can't exist there, and yet the electron half the time is there and half the time is there. Pretty bizarre, right? How can it do that? Here's one that'll, how much time have I got?
2 minutes.
Oh, man, darn it. So that was really blow your mind. I'll have to wait till next week.
Why is
It's 15
Mercury,
feet.
like, weird like that and not Earth?
Okay, good, you guys answer that. Why is Mercury weird like that, but Jupiter and Earth and aren't?
Is
They're not
Mercury
close
like
to
this?
wide.
Yeah, because Mercury happens to sit so close that it sits a little bit inside the well. And so it's, does that make sense?
So when you're this far away, like, it just like passes over the well.
Yeah.
So like
Yeah, I
a
mean,
velocity.
there's gonna be a very, very slight error, but it's not enough to be really, at least at the time
Consider
measured.
it.
So like Jupiter would have.
You should use that paper example for the next class, because that actually made it a lot easier.
Oh, good.
Yay, that was helpful.
Yeah, good. That was good. I like that. All right. Well, I'll give you some food for thought for the weekend there.